including the invention of the biaxial geogrid, followed by the uniaxial geogrid for the reinforced soil structures, and then obtained some certificates through the UK highway structures and so on. And in year 2007, there's a triaxial geogrid which used for the stabilization has been innovated as well. Okay, and 10 years after the innovation for the triaxial geogrid has been sold over the world about 160 million meters square, and it keeps increasing now. So for the manufacturing is concerned, maybe I try to put my pointer into the laser pointer. So the manufacturing of the geogrids is actually from the polymer sheet, where you go to a machine, start punching the hole, and then stretch in one direction to form the uniaxial geogrid. And if you want to do for the triaxial geogrid, which is the multi-directional geogrid, then you go to another machine and pull in the other direction. Then it is formed in one process. So these are some of the research that we have carried out, including some lab testing, including some full trafficking trial that we carry out in some of the laboratory. Later, we will go through some of this. And there are some approval from the Network Rail in UK, BBA certificate, including the EOTA and so on, which is for triaxial geogrid. And we have the quality management system certificate obtained. And BBA certificate is more for the reinforced soil structure unit using the uniaxial geogrid, where the European assessment document is for the triaxial geogrid, or we can call it a hexagonal geogrid for the stabilization purpose, which is this kind of geogrid. This is a triaxial geogrid. Can everyone see the video? And this is the uniaxial geogrid. Okay. So locally, we have obtained some local authority approval from JKR for both our RE uniaxial geogrid as well as our triax TX geogrid. And these are some of the solutions we can provide to the market, including the subgrade stabilization, optimize the pavement layers, reinforced soil structures like walls, slope, and then we have products for the rail track bed stabilization, including the embankment foundation stabilization, as well as some erosion control products. So Mr. Su also mentioned that during the introduction, there are some of these services that provided by Megajo Solutions, including all these. So maybe you can go through. So for today is concerned, we're going to go through mainly on two parts. One part is the first part, we're going to go through the use of geogrid in subgrade stabilization, and then we're going to discuss some of the case history in Malaysia. Then followed by the reinforced soil structure using the geogrid and some case history in Malaysia. So we'll start with the subgrade stabilization. So generally, there are 6 applications area that we can use for the subgrade stabilization. Number one is to reduce the layer thickness. For example, the convention design will require 500 mm thick of granular material. By using the stabilization geogrid to stabilize it, then we might be able to reduce the thickness probably by half to 250, for example. Then we can have cost saving on the material itself and increase the construction speed. The other one, if we maintain the thickness, but to include the stabilization geogrid, we're able to increase the stiffness of the pavement layer, for example. Then from here, we can increase the life. So instead of we have to do the maintenance for 5 years, we might be able to increase it to 10 years. The bearing capacity. Okay, this is in such a way that by include the stabilization geogrid, we are able to make the what we call the granular layer to be stiffer, which we call it as a mechanical stabilized layer. So with this increase of the stiffness, when the load distribution, it can distribute the load to the wider angle. Meaning to say, when the load is distributed and act on the subgrade level, it is at the wider area. So we understand that the stress is the formula of the force, which is F over A. When we have the F in constant and the A is bigger, then the stress will be able to reduce. So this is in the way that we increase the bearing capacity. So control the differential settlement. So this is usually we might use it, for example, like the road widening projects. We have old and the new pavement where always the transition area has a differential settlement problem. So usually we'll suggest to use 2 layers of the geogrid put within the subbase and the base layer, for example, to increase the fractional stiffness to reduce the differential settlement. Capping weak deposit. This is the case like, for example, I understand that like Sunway Geo or Suncon, you have a lot of project and sometimes you might encounter some weak access road where you need to do a lot of maintenance after several passes of your these construction vehicles. So by including this geogrid is able to cap over the weak deposit and then to reduce your maintenance on the access road. Spanning over the void. This is something like a sinkhole problem, but it's actually not to solve the sinkhole problem, but it will actually when the sinkhole is formed below the formation, the surface level, then it gives you some sign that there are some depression on the surface. Then we can do something in time. So this is generally the 6th application. So the history of geosynthetics in roads is that why we want to use it in road. So there are two. One is the construction access road, where you can see in this photo, a transport truck is actually sink into the access road due to the weak deposit. Okay, and so it's a very poor, maybe it's due to the very poor subgrade or insufficient thickness of the granular layer that you put in. The other one is probably on the pavement where you have a severe rutting if the subgrade is not strong enough or your pavement is not designed sufficiently. So over the years, since 1970s, people or engineers have been using geosynthetic products to overcome this problem, like the woven geotextiles, or the woven geogrids, or the welded geogrids, and punch and drawn geogrids. So there are several products being used to overcome this problem. But what we want to know today is what are the differences in terms of performance between these products, and what are the features of the geogrid that actually influence the performance. Okay, later we will go through. So beside that, maybe some of you may think, how about the non-woven geotextile? Okay, this is the non-woven geotextile where people usually use it as a separator between the two soil material. For example, you have the existing subgrade, which is a little bit wet or whatsoever, and you're going to put in some kasharan, the base layer on top of it. So usually people will include a layer of non-woven geotextiles to separate these two materials. So it's not so much on improving the ground, but it's more on separating the material to prevent the interpenetration or intermixing. So in general, there are two types of geogrids. One is this we call flexible geogrid, which you can see that this kind, or this kind, flexible geotextile, flexible geogrid. And this one usually give you a good strength. Okay, it give you a good tensile strength. But if we look at this picture, a large strain in the flexible geotextile due to the membrane effect. When the load is applying on top of this flexible material, it will have to deform, and then through the deformation, it mobilizes the strength to support the load acting on it. Where the other one is the triaxial geogrid, or maybe the stabilization or stiff geogrid, which itself is quite stiff. So maybe you ask how to differentiate the stiff geogrid and the flexible one. So if it's by visually we can see that if we take the geogrid in this way and it start to come down on the other end, then this is quite a flexible geogrid, where this one is stiff, flat all the way. So stiff geogrid, it's only undergo a very minimum strain for the stabilization purpose. So we will see more in this part, and I will explain a little bit more. So in this picture is concerned geotextile or reinforcement geogrid, where it is more on the flexible geogrid. It will require, like we explained, a deformation. When the load acting on top of it, it will form a deformation, and then to mobilize the strength to support the load on top. And this one, usually it requires the anchorage at both ends. Where for the stabilization geogrid is concerned, it does not require the anchorage because the mechanism is concerned is through the interlock and confinement mechanism, meaning to say, if this one we put below the road-based material like the kasharan and we start compact it, the stone of the kasharan will actually go and lock by the grid and then it formed the interlocking between them, and it created a very good confinement to prevent the stone from moving when there's a load acting on top of it. So this is where the stabilization geogrid work to create the interlock and confinement mechanism for the stabilization purpose. So the key performance indicator where we want to stabilize a road or want to stabilize a platform is concerned is deformation. We don't want to see a lot of deformation on the surface. We want to control it as minimum as possible, as flat as possible during the service period. So one of the indicator is rutting or maybe deformation, as we discussed earlier. And according to Professor J.P. Gerard is concerned, rutting is actually a bearing capacity failure of aggregate when a load is applying on the surface, causing the stone to migrate either laterally or vertically and cause intermixing. At the same time, it also causes the heaving. Not only on the surface, if this one is not thick enough, it may be at the subgrade level. There are some trafficking trial, we can see this result later. So in general, these are the, in terms of the difference between the stiff geogrid or the stabilization geogrid based on the interlock and confinement mechanism. And the other one is the reinforcement concept of geogrid or geotextile, which is due to the tension membrane mechanism. So on the stabilization geogrid, interlock and confinement, load spread wider, okay? So it reduces the stress acting on the surface, and the performance is improved, and it is improved immediately. Meaning to say, after you install everything, it gains the performance and it gives you the result immediately. Where for the reinforcement geogrid or geotextile, where claimed to be higher in terms of tensile strength is concerned, the load is actually when the load from the rail or the load from the surface is actually go direct onto the geogrid membrane, and it causes deformation. So this deformation it has on the geogrid reinforcement is concerned, it has to undergo the deformation on the surface first. So the whole thing will have to deform, including the geogrid membrane layer, and then the performance is after some extensive of trafficking, maybe 1 pass, 10 pass, 100 passes, only you can see the result. And the most important thing you have to keep in mind is this one only maintained when the wheel path is maintained. Okay, if the wheel path move again to the left or the right, then the whole process will restart again. So you might need to, if you want to use these concepts to stabilize the base or to improve your access road, then you might need to do a lot of extensive trafficking before you do the final surface. Okay, so a lot of maintenance need to be done in the future. It can perform also, but it performs differently. So this is how it works. Put the tri-ax geogrid below the base layer, which is a Kasharan material. Okay, so the stabilization geogrid has been used worldwide, including Malaysia, since the early days. Earlier days, it was using the square one, and in 2007, we have improved it with a better performance of this tri-ax geogrid. So the concept is we have a layer of granular material, and then we install it together with the stabilization geogrid. Then it forms a composite layer, which we usually call it as a mechanically stabilized layer, or in short, we call it MSL. Okay, so it's through the interlock and confinement. So it provides a lateral restraint on the stones, and then is at the very, very low deformation response. So the load is perpendicular to the geogrid. Okay. And the main objective of it is to protect the subgrade, so that when there's a load applied on the base layer that we put in, we try to reduce the disturbance on the subgrade due to the load as much as possible. And in some of the application that we discussed earlier, we can reduce the thickness to optimize the design, or we increase the life to reduce the maintenance. So the recent development work has provided some clear evidence of the benefit of tri-ax geogrid in stabilization, which in EOTA tech reports is mentioned. They're saying that this is a non-reinforcing hexagonal geogrid for the stabilization of unbound granular layers by way of interlock with the aggregate. So this is the way of stabilization. So TRL, Transport Research Laboratory, has carried out the trafficking trials on the sub-base quality material, which is in this setup. Generally, there's a thickness of the 300 mm sub-base with the 2% subgrade CBR. And the target ISO. ISO means equivalent standard axle, which is a measurement unit for traffic of 10,000. So in this case, one pass is one ISO. Okay, so we'll go through that. So after the passes has been recorded, so we will also record the rut depth and the deformation on the surface based on the number of passes. We can see the result. So this is some of the definition of the rutting and the deformation. So rutting is concerned, rut depth is concerned, usually after it deforms, it creates a heave on top. So we measure from this point to the base of the deformation, and this is called rut depth. Deformation is concerned is for the original level to the base of the settlement or the deformation. And the difference between these two is actually the heaving, the heave. So this is a setup of the trowel. So there are two sections we are carrying out the trowel. One section is using the stabilization geogrid based on the mechanical stabilization via the aggregate confinement and interlock. The other section is using the membrane type of geosynthetic material, which is with some good tensile strength. And the subgrade and the granular layer thickness condition are identical. Okay, and this is a section show on the stabilization geogrid, which we call it TX, and the other one is MEM, means membrane. Okay, so this is the thickness of the 300 mm granular layer. This is the surface, and this is the subgrade surface. So we go through the result: 1,000 passes, 4,006 passes, and we start to see that the blue color one is actually representing this membrane effect, and this is the measurement measured on the surface. When it's up to the 4,600 passes, the deformation is about 110 mm, where the rutting is concerned on the membrane section is close to about 200 mm, which is quite severe. And the test has to stop at the membrane section because the wheel cannot contact anymore with the surface. Too deep already, the deformation. So we carry out again on the TX section. The red color one is TX section, where we can see that both the rutting and deformation almost overlap, so meaning that it's not causing the heaving. So the confinement or the TX section is continued up to 11,500 passes, and from this result on the surface is concerned, we can see that it's a very minimum deformation has formed, and almost no heaving at both ends here, meaning to say the rutting is not severe. And on the subgrade level is concerned, as we can observe, it's not much changes on the subgrade level as compared to this one. So these are some of the results in summary. So we can see that we improve in terms of the life, and we improve in terms of the performance. Okay. So maybe with this design, we can reduce the thickness. So the other one is carried out by the US Army Corps of Engineering. And this time, not only the sub-base, the base layer, we also included in a layer of the asphalt concrete, which is 50 mm thick. And then to see what is the result will come out. So in this one, we are comparing one with the stabilization geogrid, with the other one is without any geosynthetic material. It's just a control section. And we reduce the base thickness to 200 mm, and the subgrade CBR is concerned, we increase slightly to 3%. Okay. This is a setup of the test, and this is a wheel acting on the surface. Okay, and this is to show you some of the result. So the blue color line is the 50 mm thick asphalt concrete at the control section. The red color line is the similar section, 50 mm thick of asphalt concrete as well, but we include additional layer of TX, the stabilization geogrid in the section to run through the test. So at the same time, we also increase at the control section, we increase the alpha-stick concrete layer by another 25 mm to total thickness of 75 mm to see how much it will improve as compared to the stabilization geogrid. So let's say we take the 20,000 ESOs as a line, and then to look at the deformation. Okay, so 20,000 is concerned, when you look at the control section with 50 mm thick of AC, we will see that the deformation or the rut depth is up to nearly 50 mm. If we increase the thickness of the asphalt concrete layer, then we improve the performance by quite significantly to 20 mm of rutting. However, if we look at the 50 mm, same with this one, but with the stabilized layer of TX 140 geogrid, we are able to reduce the rutting to less than 10 mm. So this is again a proof from this full trafficking test where it improved in terms of performance. So after they complete the test, they would like to know what we call the condition of the testing layer. So they actually cut down. As you can see, the red dot on the surface here. This is the control section, and you can see the red dot on the surface here is undergo a very severe rutting. Okay, and not only that, we can see that the thickness within the granular field is concerned is been reduced, especially at this center part where the load is contacting. Where this one they squeeze the stone, and then this one becomes thicker, and there's a significant, there's a very significant of the deformation on the subgrade level. So they also dig up the base with the stabilization geogrid. So from this section is concerned, even though with the higher ESO, meaning that more passes they run through the test, we can only observe a very minimum deformation or rutting on the surface, where almost none, maybe slightly over here, which is on the subgrade level. So this is some evidence that shows that the difference and the improvement can be achieved by the stabilization geogrid of Tri-X geogrid. So we retain the aggregate thickness and the shape of the pavement layer. So if some of you still cannot catch the idea of interlocking and confinement, maybe I give you an example by using this snorkeling rack or snorkeling frame, snorkeling ball frame. We start stacking up the ball in this way and form a pyramid. If we put a load slightly on top of this, everything will hold in place. And that is due to the confinement at the bottom by the frame, and then the interlocking between each other. How about if you take this frame up? If we lift it up, then the whole thing will spread and then move over. So this is the idea of interlocking, where you can show, can be representing in this diagram. So what are the properties, physical properties, for example, that actually influence in these types of performance? So one of the important property on the geogrid itself is the rib profile. So some of the rib, for example, like this kind, okay, so the rib profile, as you can see, that it is very flat, okay, and at the same time, the junction is concerned. This is called the junction. It's very flexible. If you put it this way, although it's good in strength in the main direction or the cross machine direction, but in 45 degrees, we can see that the whole thing is actually very flexible. So if it's flat, so it's unable to interlock or unable to confine the stones well, because when the force applied, the stone will push to the sideway and then it will tend to roll over. Okay, where for the stabilization geogrid is concerned, we can see that the rib has certain thickness, as a kind of thickness, and it's important that it is a rigid junction, which give you a very minimum movement, okay, and very stiff material. So when there's a load applied on the stone, it will actually hold and lock with and confine by the grids, and especially near the junction where it doesn't move. These are some of the properties that summarize what we have discussed just now, and probably you can read through it. There are a few that I would like to mention. Mechanically, stabilization layer is concerned using the stabilization geogrid undergo a very low or small deformation. Okay, where for the tension membrane, it will need a large deformation to mobilize the strength. Then anchorage length is concerned, doesn't require, it is not required for the stabilization geogrid, but it is required by the tension membrane type of geogrid, like the reinforcement type of geogrid. Then the pavement rutting is usually very low, and this one it will be very high, and you need, like we discussed, you need to go provide some maintenance before you release it for the public to use the road. Okay, so these are some of the important notes that we'd like to highlight to you. So in this slide is concerned, I'd like to show you a video where you can see the heavy truck is running on top of this access road where the subgrade CBR is relatively quite low at 0.5. So they put a layer of stabilization geogrid with a thickness of the base layer 300 mm and the truck with the weight of 50 ton of load running through of it. And at the end of the second section is concerned, they take out the geogrid, everything maintained the same, but they take out the geogrid. So you can see the difference in terms of performance. I would like to play the video right now. Okay, it works. Okay, so we can see that at the end, when the truck has moved to the area where it is. Okay, so we can see that at the end of the video, the truck moved into the section where it is without the stabilization geogrid. It gets stuck. So in this situation, the mine operator might need to maintain the access road quite often, which is increase a lot of their operational costs, at the same time reduce the productivity. So that is the thing that you need to consider. For example, if we use it for the earthwork project site. So this is not only apply for the soft ground, it can also apply at the higher in pavement or access road. And the geogrid tensile strength is not a reliable indicator for the performance because this is not the reinforcement. We understand that if it's reinforcement, then it needs to undergo a large deformation, then it causes a large rutting before it can give you the result that you are expecting. So this is again another video about 3 minutes that we like to go through, which is for the installation of the this stabilization geogrid. We do not require any special equipment. It can be done using the conventional method, using the conventional machineries for the road construction or platform construction or access road construction. So we will go through and have a look on the video. So we can just unroll the geogrid by using the labels. Some strong man, one person can handle. One put the 2-man problem. So what we need to do at the edge of the geogrid is that we need to provide just overlapping, minimum of 300 mm, 600 mm, depending on the condition. So this angle of geogrid doesn't mean the anchorage length, but it's more of the just to hold the geogrid in position. So usually we recommend you put a structural material to hold. Yeah, it's not recommended to drive the track directly on top of the geogrid because it will damage. And if you want to do it, then you place a minimum thickness of 150 mm of the base material cover. So it depends on the construction equipment of type. You can use a picture with this type of scaling. Then the compacting will be still the same, require the same requirement based on GKR requirement. So after spread it, you just need to compact it based on the layer thickness specification. GKR or maybe by the consultant. So this is just as simple as that. At the same time, it can give you a very superior performance if we consider both the commercial part. That's it, and we'll proceed with our presentation. So now we will go and have a look on some of the case history in Malaysia. One of it is the Sam Sembawang Engineering Fabrication Yard in Pasir Gudang, and this one I think is in the year of 1987. This very early day. So it's in the whole area is about 7 acres, and the soft clay alluvium up to about 10 meter deep. And there are some residual soil which is on top by 1 to 2 meter. They top up over the times in their previous maintenance. So what they want to support over there is actually lifting crawler cranes ranging from 200 tons to 250 tons of load with a contacting pressure up to 500 kPa. And they want to prevent some severe rutting which they experienced before, so they contacted us. So what we have proposed to them in those days is the 2 layers of the stabilization geogrid used as a repair scheme. So this is the condition of the fabrication yard before the repair, and this is the size of the machine. Later we have a closer picture to view of it, and this is the some simple cross section that we propose. The whole thickness is about 1 meters, and we build it about 300 mm above the original level, where to allow some settlement, total settlement, I would say, in the future. And this is the installation. Is very simple and fast. And upon the completion, this machine worked perfectly well on top of the surface. And the client is quite satisfied with the overall result, where they don't have to carry out the maintenance that regularly. So the other one I would like to discuss about is the temporary access road and working platform used for the project site in Shah Alam. So we propose this tensile mechanical stabilized area in that. So we were called by a contractor where they are tendering for one project, and they want to reduce their cost and maybe to increase the construction speed during the preliminary, to do some temporary works like access road and so on. So they contacted us to go in to propose them a temporary access road. So they have given us some SR results. So from here we can see that the top layer is about okay, but we have a medium layer, the middle layer, which is quite soft. So quite identical for both of the borehole. And this is a sectional view of the soil condition. The first 1.5 meters, we have loose sandy sand with M value more than 7, and then followed by another 9 meter thick of the very soft clay, where the M value is only 1 to 2. Okay, so you might say that some of you may think that then it's okay to work on top of it. Exactly. The contractor also told us what they plan to do is that they will use a top layer to do the piling works. So upon they finish the piling already, because in this project they are required to build the basement. So they need to excavate down to build the basement, but they face a problem when they dig it down to build the basement. They have a very soft clay layer over here, and they cannot have their heavy working machinery to sit on top of this. That's why they need an access road. For example, for their concreting works and so on. So there are some other options they also consider, like the stone column, deep soil mixing, R&R, to improve the formation level for the access road. So the proposal come from us is to stabilize the access road by using the stabilization geogrid. So at first the whole area is about 5,000 meters square, is not much. So after hearing from them, so we say that, Mr. Contractor, why not this way? We propose you something where you can allow your this piling equipment straight away work on this soft layer. At the same time, you have this concreting works and everything done at the same level, and it will save you a lot of times. And I believe in terms of cost, it will give you some saving as well. So we propose to them, and then they are quite happy with the proposal. They accept it, and they have given us this is the piling rigs information, which is the weight is up to about 100 tons with some track dimensions, which is we use for the design. So in general, we propose 2 layers of stabilization geogrid, PX160 geogrid, with the total thickness of the granular, the Kasharan layer of 550 mm. So this is the track pressure acting on top of the surface, which is about 200 kPa. So this is a picture show the condition on the surface, which everything was good, and you might see that there are some road over here. Yes, the client actually bought over some existing factory where they want to convert it to the business center. So this is where you can see some perimeter road was built earlier, and that is also explained why the top layer, the 1.5, is better than the lower layer, because that has been treated before. So when the excavating down for this approximately 1 meter plus, still okay, but they go further down, you can start to see that the grayish clay material, which is soft. So the contractor also concerned about the performance, because they first time use the system, and they say that our proposal and idea was fantastic, but they are not sure about the performance. So what we recommend to them, they carry out a trial on the critical section. So what they do is that they build a small section for the trial with a width of about 7 meters and length about 20 meters. And they start putting everything in according to the proposal that we provide. And this is the ramp coming down from the top platform and go to this trial section, trial platform. Then they keep loading it. We were not invited to this trial because they want to do it themselves, so that it is independent according to them. But we can see from this picture is concerned, similar to the Canada oil sand mine, where after the stabilized section, we see a very severe rutting on the surface here. Same lorry, same number of passers, and this is perfectly well. This is having some severe problem. So with that, it gained the confidence, and it gained it gave a very good result to the contractor, and they start buying in and start install for the rest of the site in the area which is required. So the good thing of this stabilization working platform is concerned is that during the installation, you can, those area that is already complete with the installation, you can straight away carry out the construction work at site without any curing period or any stabilization period, for example. Because as we mentioned earlier, this gives you the stabilization result immediately. And so after the full installation, this is a condition of the site construction activities. So another one, we use it to stabilize for the road and undergo some very difficult ground. And this project is in Forest City, Johor, by this China developer called Country Garden. And they want to build some temporary access roads so that they can allow the buyers to go into the reclaimed island in the sales gallery to maybe buy house or whatsoever. So they want to do something quick. So what we have proposed is multi-layers of the MSL stabilized by the Tri-X geogrid, and it go through some of the mangrove swamp area without any treatment on the base. It's just to remove the rubbish and remove the trees and whatsoever. So it was built in a very fast speed. So it allowed, this is already completed. So it allowed the buyer to access into the island to look for the houses. And this is on the reclaimed island. Okay, so the entire length is concerned is about 10.5 kilometers. One side is go to the island, the other side is go to their golf resort. So this is the condition of the island. We can see that these are the road all stabilized by the geogrid. And they also did the planning where in some section of the road they use it for the construction access. So this is one of the access. Underneath there are some geogrid stabilized the granular layer. So after several passes of this type of construction vehicle, we can see that the condition of the access road is quite well. Besides, there are a lot of dust on top of it. That's it. So the kind also think about how about other types of product? Can we use that to achieve the same performance or same result that we want? So they also get in some reinforcement geogrid, which is work on the membrane with a higher tensile strength, and then they start apply in one of their section. So after they complete the surface layer and there are some what we call the transport truck moving on top of the surface, immediately the rutting form on the surface. Okay, immediately so as compared to this one, after several passes, we don't see severe rutting. But this one, after few passes only, maybe one or two, we can see that it's already some rutting. And this again proves that it needs a deformation for this kind of geogrid to performance. So it need to carry out the performance. So after this one, they are not satisfying with the result of this membrane geogrid or the high strength geogrid. So they go back to our tri-X for the rest of the works. So this is to show you the interlocking and confinement at the boundary of the separate on this part. This is a geogrid, and we have another layer of geogrid here, actually by 2 layers. So we can see that although this is moving very near to the edge, so it is only a little bit movement of the stone over here, but you don't see any movement of the stone after the first layer of geogrid. So this is again interlock and confinement, although it's a very huge solid on top of this. And this is the completion of the road. And the other one, they want to build the IBS factory nearby the construction site, and they bought over some mangrove swamp land and then convert it to the factory. So they just simply do the earthwork, and then they start to encounter the problem with the access. It's very messy. So they call us in. And get the parameter road done. So this is the difference between the stabilized and the non-stabilized, and this is the completion. Okay. This is a completion. Go through a little bit faster because I see that probably the time is maybe not that sufficient. So we can use it for the storage yard as well. We can use it for the track bed for the train. And as mentioned by Mr. Sudi, it's not something new. Since 1985, we started the first project in Malaysia. So that is more on the stabilization. And now we go for the reinforced soil structures with geogrid. So this is totally different from what we have discussed just now. This is more on the structure where we require the geogrid with strength. So in 1986, we built the reinforced soil structure vertically without any facing by the wrap-around technique in this Normal Memorial Medical Center, Kuching, Sarawak. And it finished with the surface of the turfing. It is only used for the temporary during the plan in those days. So this is the type we are talking about, uniaxial geogrid. And the concept is very simple. They put in layers of geogrid in the different level of the soil and then compact it. So the construction technique is not much different as compared to those doing the earthworks. So there are wide variety of field types and facing technique can be used. So the idea is that when we build the structure, when you go near as vertical as possible, it always has a critical slip surface. So this critical slip surface at this zone is concerned, we call it as the active zone where it tend to fill. So what we want to do is that we put in the reinforcement geogrid, encroach beyond the critical surface to increase the frictional resistance. So it improves the factor of safety through that. So this is the whole thing we call the reinforced soil structures. So types of structure, we can build purely on slope, walls, or the combination of both. Okay. So for the slope is concerned, these are some of the facing type. Usually for slope up to 45 degrees, there's no wraparound facing is required. We do already trim the surface and then we turf it. For the wraparound, usually we need a backwork or some formwork in front of it. Sometimes we use a steel mesh to form a formwork in front of the surface so that we can do the compaction during the construction of the reinforced soil structures. So this is the slope with up to 45 degrees where the geogrid only plays horizontally up to the facing, okay, all the way up, and then this yellow color one representing the soil, compact all the way up. Okay, some of the structure can be built this way. If we need to have structure which is at steeper angle than 45 degrees, for example, in this picture, 70 degrees, then we will need a wraparound technique with some facing, like in this case is a backward. So we put the geogrid, we wrap it up, compact ready, connect the second layer of geogrid to this blocking joint as shown in this picture, and construct all the way up. Of course, retaining wall, and we can use a segmental block, which we call it as keystone retaining wall. So some of the project which is maybe out of the city, we can use some gabion facing, but we can reduce the numbers of gabions by reinforce the gabion. So it's a rock face wall. So in design is concerned, we always need to check on the internal stability. We want to make sure there's no rupture failure, there's no pull-out failure. And external stability, we want to make sure that all these will not happen in our design. So during the discussion, usually we need to discuss through quite a lot of questions with the consultant and then get the requirement from the client on what type of facing they want and so on. And then we can decide the structures that we want. For example, if we go for the wall, then this is some of the wall design. And some you may ask what kind of length that we need to provide for the structure. So usually, according to the code, is 70% of the height or some minimum geogrid length is required. So there are a lot of the design program available in the market. So for us, we have in-house program to carry out the design by putting all the information in and then carry out design to see what type of spacing and geogrid to be used. And we produce the drawings for the construction site to carry out their works at site. So these are some of the possible failure mechanism as we discussed earlier. So pull-out failure, rupture failure, and then for segmental block is concerned, we also need to check on the connection failure. So this is some of the long-term sustained load tests that we carry out in the lab, is to check what is the creep rupture strength that can be achieved by different type of geogrids. And because all this geogrid is HDPE material and it's a polymer material which is quite sensitive to the temperature, so we have to carry out it in the different temperature. Like for example, then we understand that in Malaysia we need to apply a 30 degrees Celsius or 25 degrees Celsius for the tensile strength in our design. Okay. So after applying it, we need to determine the the design strength, the long-term design strength, by applying some of the partial factor like manufacturer partial factor, site damage, and environmental. So for this uniaxial HDPE geogrid is concerned, it's not so much on these two, but on the site damage, it depends on the granular fill material or the fill material that we fill together with the geogrid. So we carry out some tests on the real site, and based on the different type of the fill material size, and then dig it out back to the lab and do the testing to see that how much it reduced as compared to those in original to determine what is a partial factor. So we have to make sure that our geogrid is actually can resist against all these chemicals like acid or alkalis. Is particularly important in our country, tropical climate. So some of the polyester, like this one, is actually the HDPE. HDPE usually is quite okay to resist all kind of chemical. It has a wider pH range, but this type of polyester grid is concerned, then there's a huge concern over the pH and the high temperature. So during the design, have to check with the manufacturer and then apply the correct partial factors. So the BBS certificate has actually discussed some of these important partial factor and some properties in their certificates. so that we can find out depend on the products. So we'll go through some case study. This is the cut slope failures, which happened 2008, if not mistaken. It is in Sunway Monterrey, is a Sunway project. And we can see that after some repair, the slope failed again. So this is one end, this is from the other end. So these are some of the repair with some gabion wire mesh kind of material. And you can also see that some structure has been built before, and this is the degree of the failures. So we were invited in to give our proposal in the tender, and what we have proposed is a 2-tier keystone wall, followed by the 2 reinforced soil slope on top of it to reinstate back the slope. So after everything is checked and went through with the client and the consultant, the construction works begin with the construction of the keystone wall. Okay, this is a construction and can erect very fast because it is not involve very much wet casting work at site. So upon finish of it, build the reinforced soil slope is concerned, usually we will provide, which we call it a rock toe. So this rock toe is a good detail for the slope construction where it prevents the toe softening. So of course, behind of it, there are some sand drainage layer and some PVC pipe to allow the subsoil water being discharged and then discharged through the surface drainage system. So this is the end of the product. It's still standing until today, very good in terms of performance. Besides, I think there are a lot of big trees grow already nowadays. It's very near to the corner houses. If I'm not mistaken, it's probably about 6 to 10 feet. Okay, so this is a way of reconstructing. So we have also done some keystone wall in Taman Desa, which our main contractor is Sunway Geotechnics, supported by the Geopier. Okay, and wall has been constructed in that project is a Faber Union project in Taman Desa. So besides using it as a retaining structures, so we can also use it to gain some extra value in terms of landscape, for example. So we can use it as a lake lining, and then of course this some great work by the landscape architects. So we can have something like this, and always for keystone is concerned, you can create a very smooth curve where it looks not that structured. So some covered crossing over the rivers as well as the traffic. We use it to build to cover some bridge as a bridge embankment, also to cover some bridge pillars. And this is the building up, and this is the completion, and this is the field embankment, and we can join it back together with the keystone wall over here. So if we need to build some high wall, we can usually we can do it in tiers. Okay, then it doesn't look that the structure doesn't look that huge. And the good thing is that we can have a very, not that sharp, but a very good corner, very smooth turning, where to create some good wave. Maybe it's good for the housing development. And this block, because it's quite small, is about 40 kg per block, so it can be carried manually, and then it can be done in some of the narrow space. Okay, so in geogrid reinforcement construction, there's also a technique called hybrid construction where it combines the geogrid and the soil nailing. So this is a slope failure project in Smokehouse in Fraser's Hill. And we understand that this, I never stayed there before, but I know that it's a very old building, 1937 built. And then due to this failure, the part of the building has actually collapsed and damaged. This is the condition of the site if you're looking downwards, and there are some extension works that have been done over the years, and maybe also part of the factor which caused the failure. So when we did the site visit is concerned, we see that a lot of piping connecting here and there, and the water also discharged everywhere, and it's discharged towards the slope area. So this is the main factor that caused the slope failure. So what we propose is reinforced soil slope, and then we have some toe wall. In terms of section is concerned, look, in this line is concerned, we have the building. So if we only put in the reinforced soil structure in this way, it's not sufficient enough to improve the factor of safety in overall. So in this hybrid construction techniques is concerned or design is concerned, we combine both the geogrid reinforced slope and the soil nailing. The soil nailing use it to improve the factor of safety within the housing area where we cannot excavate the soil. So we can only remove whatever is loose, and then we build up this reinforced structure to give them back the platform on top of this. And this reinforced soil structure is stable by itself, and then we transfer the loads through the micropile foundation below it. So this is a condition of the site, access road, carry out the SI, and then we commence the work with the micropiles, construction of the slab, then followed by the soil nailing, and of course soil nailing pull-out test. And one of the part I would like to mention in the level where there's layers of this soil nailing, we also connect the grid so that this grid is able to transfer the force to the soil nailing area, and then it transfers deeper into the ground. So to improve the overall stability to this way. And this is actually connected through a blocking joint that we go through, I mentioned earlier, through the grid, and then we place this GI pipe behind the plate of the nail. Okay, so compaction is done, and we can see that the surface here is loose. It's always a good practice to to carry out the construction of the slope by compacting the earth slightly beyond the surface that require, the surface profile that require. So we can compact here up to a certain level, and then we trim it back. So after we trim, this surface is all well compacted. So it can be seen in this way. This is already trimmed, and this one is not trimmed yet. So you compact up to another level, and then you trim it again. Okay. Surface drainage system, cascade drain, and then turf. And this is the picture before and after. I just go through. Okay. So provide. So all the drainage, surface drainage is important. So we improve quite a lot in the drainage system. And then we also provide some walk path so that the visitor can come in here for the bird seeing. They have some kind of event of bird seeing every year in Fraser here. Then this is a Pan Borneo highway project. We are using this to build up the road embankment, which is up to 30 meters high. And this project is still ongoing at site right now. And this is, I think, it's about 3 slopes has been built already. This is some section, show a closer view. One height of each slope is about 5 meters, followed by the 2-meter berm, and every berm provided with the surface berm drain. Some rock dome is provided and reinforced by geogrid all the way up. And in Middle East is concerned, they have using this technique to build a very huge structures. So it's actually connecting a road from this hill to the other hill. So this is very somewhere out of the town, and they cannot get the concrete easily, and maybe also because of the temperature over there. So what they can have over there is they have a lot of the backfill material. So they decided to build these reinforced structures. So we can see here there are 3 tiers of wall. The 3rd tier is still undergo the construction. Each tier of it is about 20 meters, 20. So the total height is about 60 meters. And this is the end of the construction, and we can compare. This is the size of the trucks, and this is the size of the structures. Okay, look from the back. And reinforced soil structure concept actually is not something that is very new. In very few thousand years back, people already used this concept to build a structure, which is the Great Wall of China. We can see that they also use something like a segmental block kind of facing, and then they put in some fiber material layer by layer to reinforce the soil. Of course, if we from the picture, we can see that the layers of the grass or fiber kind of thing is very close spacing. So they use this technique to build the Great Wall of China. And I think this is probably the end of my sharing session, and I hope that all of you can get something. And is there any questions?
Mr. Chan, this is Thomas from Sunway.
Hi, Thomas.
I would like to ask a question in relation to, for those projects where you have employed it on the slopes.
Mm-hmm.
And you show a lot of subsoil pipes being put into the slopes to drain the water. Mm-hmm. Okay, because I believe this is a key aspect for maintaining the stability.
Exactly.
How is it then going to be for maintenance during the maintenance period to ensure the life during the design life of this for this project?
Okay. So for the subsoil drainage is concerned, usually we allow it in every berm of the slope. So we have the combination of the rock toe, which is the facing of the toe to prevent the softening, the toe softening. And then we have layers of the sand. We have layers of the sand. Maybe I go back to some of the slide to explain in this one. Yeah. So we have a layer of the sand at the base here. Usually is 300 to 600 mm thick, and to drain out the water. Then followed on top of this, we have the same column. And this, we call it as a column because we don't continue the sand layer at the back of this slope here continuously. So we do it as a column at certain interval, for example, 3-meter intervals or 5-meter intervals. So in terms of maintenance is concerned, actually it's not very much within the soil itself, because the pipe, the PVC pipe, actually is helped to accelerate the drain of the water from the slope itself. Even the sand layer is able to drain away the water, not only just the pipe. So it's on the maintenance itself is very much on the surface drainage, especially after the pipe is coming out or the water is going into the berm drain. Usually we will have the problem where people never carry out the routine maintenance for their berm drain, where the berm drain get covered by the vegetation, or you have some settlement between the concrete and the soil, and it causes the water to seep through underneath of it. This kind of maintenance need to be carried out on site in routine, maybe 6 months or 12 months a year. And it's not only apply for these reinforced soil structures, it apply for all the slope constructions. So it's more on the surface drainage system, I would say. Yeah, I hope I answer your question, Thomas.
That's perfectly fine. Yeah. So what do you suggest is the best way in which we can work with companies like you?
Mm-hmm.
How do you suggest it going forward?
Okay, usually our company provide a total solution, meaning that if you encounter some project, maybe it's a reinforced soil structure, you want to build a brand new reinforced soil structure, or you encounter something like somewhere in Mount Terrace where you have a slope failure, then you can provide us the information. We study the information, we work together with the consultant in terms of some technical parameters, and then we submit our design proposal. After we get everything done on technical, then we can be appointed by you as a design and build contractor for these particular structures. So because we also provide the design and build service. So usually it can be worked in this manner. And we have been using this manner to work with a lot of the clients or some contractors where they need counter proposals sometime over the years, and it worked perfectly well. Yeah. Any question?
Going back to your solution for where you want to create stable platforms for equipment to work. Okay. I mean, this is temporary work. Yeah. In what kind of situations do you forecast that your solutions are probably better than maybe other solutions that we have currently? Under what circumstances, general circumstances?
Okay, maybe we use this case to discuss about it. It's a short alarm case. So like in this case is concerned, we see that we have 3 layers of soil at site. One is a capping layer, which is with a thickness of 1.5 meters. The other one is a soft clay layer with a thickness of 9 meters. followed by some medium dense silk layer. Of course, for temporary access or working platform, we do not require too much to consider about this because very much will actually taken place in this layer. So back to your question, when we want to consider whether geogrid system or whether some other system. For example, if today you have a site with a soft clay layer only with about 1 meter to 1.5 meters, then you might go for the method like remove and replace. Probably it will be cheaper and it should be cheaper. But if today you have a case similar to this, where you have a 9 meter thick of the soft layer, if you carry out R&R, for example, another 2 meter below here, then you need to excavate a lot. You need to deal a lot with the excavate and export. That's one part. The other part, you still have some soft layer below you. And if the equipment is very, very heavy, whether the 2 meter is sufficient or you need to go more like 3 meter or 4 meters, that kind of thing, because you still have the soft layer below you. So this is one of the consideration you might want to consider. Then method like we mentioned earlier, like stone column, deep soil mixing, that will be very much on the cost comparison, I would say. And in that case, geogrid solution certainly is cheaper than that kind of solution.
Okay, anyone else has questions for Mr. Chan? I think the presentation is excellent. This is what I expected from Mega Geo Solutions. Yeah, I think it shows that there are many ways in which you can deal with the situations that you're presented with. It doesn't always have to be a standard solution. Yeah.
Yes, right.
Okay, I mean, I know your colleague, Mr. T, for the same amount of time as Mr. Su knows him. Huh? Yeah.
Wow.
Yeah. Okay.
Wow. Just now they were mentioned about 1985, 1987. Those days I was only something like 3 years old, 5 years old boy.
Okay. Okay. Do any of my colleagues in this webinar have any questions for Mr. Chan? Please don't feel ashamed. Huh? I mean, I think we will be meeting Mr. Chan and Mr. T much more in the future. I have a feeling.
Very good. Thank you very much. I mean, Sunway Geotechnics has been always our good partners and good client that we work together for quite a lot of projects. It's just that recent year a bit quiet. So I think probably we can take this opportunity to restart back the engine.
For that, you have to ask Mr. Su what happened, you know.
Yeah.
Okay. Ask PIC, because like in this case, maybe the PIC for LRT projects they are facing some soft building clay problem. So I think Tensar maybe is one of the solutions that should consider, you know.
Yeah, we can study the problem also. So
whether for the piling platform or in the future when they're doing all the pier, all these things, because at the time they may need to use a lot of heavy machinery like 200 tons crane, all these things, I know.
Yeah, correct.
Because I think that what have been successfully doing is some Bawang projects they are using a 200 to 250 tons cranes, you know. That means he can sustain a very high machineries on those soft marine cranes, you know.
Yeah.
So maybe this is the thing maybe we can consider.
Well, you know, in this webinar we have people from various business units within Sunway listening in, and I hope that with this discussion, people will take the general advice that we have given right from the start, which is bring your problems to level 7. We will act as a one-stop agency, and we have the network of our business partners and with our own in-house technical department, and we would be more than happy to propose those solutions.
Yep.
So because we can be a very neutral party in proposing, in the beginning, yeah, and then we can get our business partners involved.
Yep.
So I do not know why my colleagues are very shy today. We had at the peak, I think, something like 86 persons following this webinar.
Excellent.
I think it has been a very good response.
Yes.
So
thank you
if there are no further questions, I hand you back to Mr. Su, and Mr. Su, please do the needful. Are you by any chance sharing this presentation, the PDF
sure,
format?
I can share it with Mr. Su
Yes.
later. I will convert my slides in PDF so it's easier.
Yeah, you convert it to PDF and you send it to us, and we will send it to everybody in our distribution list. Yeah.
Thank you very much.
Yeah?
Thank you very much.
Mr. Su, you please take over.
Okay.
Thanks, Thomas.
Okay. Thanks, Engineer Chance, for his impressive presentations. I think a lot of us will gain a lot of information from this presentation. We hope we can discuss the things in the future. Okay. Yep. Okay. Thanks a lot, Mr. Chan.
Thank you very much. Thank you.
Bye.
Okay. I would like to remind all of our colleagues on this group chat. This is webinar number 17, presented by Sunway Geotechniques. We have another presentation, number 18, on Tuesday, which is 21st April afternoon. That will be run by Sunway Geotechniques, which is best practices in foundations, deep foundations. But we are only dealing with deep foundations in that one, best practices. So I look forward to meeting all of you for that presentation on the 18th. Thank you very much.
Okay, thanks.
Okay, thank you, everybody. Bye-bye.
Okay, bye-bye. Thanks.
Thank you.
Thank you.